Hello everyone, good evening. Welcome to the course of Nanotechnology Science and Applications. This is an NPTEL 8-week course in which you will be introduced to nanotechnology, nanomaterials, the science behind nanotechnology and nanomaterials, and finally its applications in various sectors. The course coordinator for this course is Professor Pratap Haridos from IIT Madras, and I will be the teaching assistant for this course. Once again, to remind you of the doubt clearing sessions. Um, in these sessions, I will be answering to all of your queries, and I will be going through some of the lectures, like briefly, not in details, which will help you to tackle the questions in the assignments. uh, this time the course in this week the course pattern is a bit lighter, like everything was covered by Professor Pratap Haridos, um, and the questions were directly put up from the um, uh, the- from the teaching materials what he taught in the class. So, yeah, just to give you a brief idea and to just wrap up what Professor Pratap explained in this course and in this week. And finally, just to give you an idea about various types of things which we need to focus into this week's course. So, I'll be giving you a brief idea. This is a very short, today is a very short course. I will not be extending it more than 1 hour. So yeah, feel free to ask any questions if you face any problem. So just a recap of the previous session, what we learned in the previous session. First, the our session started with the definition of nanomaterials, like what material we consider as nanomaterials, or what is the proper definition? What class of materials can we consider as nanomaterials? That is, in nanomaterials, at least one of these dimensions in these materials is less than 100 nanometers. That is the only thing which is required to consider it as a nanomaterial. Uh, And on this, based on this definition, the nanomaterials are categorized into various types. Like you can say that I have said that the definition of nanomaterials is like at least one of the dimensions is less than 100 nanometer. So one can say that there may be multiple dimensions less than 100 nanometer, all the three dimensions less than 100 nanometers. Then it's called zero dimensional. Only two dimensions are less than 100 nanometers. That is one dimensional. Similarly, two dimensional and three dimensional nanomaterials. Then finally, we discussed about the synthesis of nanomaterials. Like, what is the main aim of synthesis? Uh, Synthesizing a material, that means you want that material to be highly pure. But the problem with nanomaterials is that the surface area to volume ratio is quite high for nanomaterials, right? Because the surface area is quite large than the volume. Therefore, this makes the nanomaterials quite unstable. Like they want to react with each other because they are very free, they are highly free. Their is energy present in nanomaterials is too high, so they're highly excited. They want to just coalesce among each other and to react with some other material because of the surface to volume ratio, higher surface to volume ratio. So the synthesis of this material is challenging, and synthesis we require the material to be pure. And in so the main aim of synthesizing nanomaterials is to get an identical shape and composition, identical shape and morphology, size, composition, and monodispersed particles. This is quite difficult to achieve. And on the basis of these synthesis, we have two types of methods. One is top-down approach, one is bottom-up approach. What is top-down approach? material at a higher scale, we are breaking down into lower scale or nanoparticles. That is top-down approach. And bottom-up approach, material at a angstrom scale or lower than nanometer scale, then we are scaling up to nanometer range. That's called bottom-up approach. Then we learned about the advantages in bottom-up approach and advantages in top-down approach, disadvantages in both the properties, both the manufacturing techniques. Then finally we understood, okay, now we got to know, okay, how the nanoparticles, what are the nanoparticles, how are they produced? We got to know about that. Then we said that nanotechnology or nanomaterials, the properties are different in the nanoscale. We always say that. Otherwise, if you're not getting a difference in the properties in the nanoscale, why were you studying that? We should get any difference in the properties. That is the main reason for studying that, right? So nanomaterials change the thermodynamics of the material particle or the thermodynamics of the system. And as we learned, thermodynamics and kinetics change the microstructure of the material. What is microstructure? The uh, the microstructure of the material is the thing which you see under the microscope. When you etch the sample and this, you see different types of things on these phases, different types of things. By things, I mean phases, different crystallites, different what do you call precipitates, different types of things you see in the material. Those are known as the microstructure. And thermodynamics and this microstructure is dependent on the thermodynamics and kinetics of how the material is produced, or what is the stability of that material, how the material is stable or not. It is dependent on that. And nanomaterials change this thermodynamics and kinetics. So this implies nanomaterials change the microstructure of the material, and all the properties of the material which we get, like hardness, ductility, anything, is highly dependent on the microstructure of the material. So if we change the microstructure of the material, the properties will change. That means in turn the nanoparticles changing the thermodynamics will in turn change the properties of the material. Properties may be in the higher side or the lower side, we don't know, but it changes the properties of the material. Then we learned about Hall patch strengthening unit, how Hall patch is valid in micron scale and micron below the micron scale in nanoscale. In micron scale, we are following Hall patch relationship. That is, the yield strength of the material is inversely proportional to half of the grain size. And when the grain size of the material increases, that means the strength decreases because they're inversely proportional. So when the grain size of the material is smaller, the yield strength increases. This is known as grain refinement, strengthening due to grain refinement. But this is valid up to a limit, that is 1 micron. And above 1 micron, it is valid. Below 1 micron, a different type of technique or phenomenon comes into play. That is grain boundary sliding. And due to this grain boundary sliding, the phenomenon of grain boundary strengthening, which was observed there, is not observed in case of particles with grain size less than 1 micrometer. The materials. The question is, are microstructure materials same as nanomaterials? Uh, I couldn't get the question. Microstructure is different, nanomaterials is different. I think your question may be, are micromaterials same as nanomaterials, right? Can you just explain me the question? I couldn't get the question what you have asked. Okay, yeah. So microstructure materials are different. Of course, they are different from nanostructure materials, because the thing is, as I have told you here, that the grain size, the grains, every all the properties of the material depends on the microstructure of the material. And you can see here, This grain size is different in case of micron size material and in case of nanomaterial. What happens in case of nanomaterial? The nano grains are in nano range, right? That falls in this range. But in case of micron size material, they fall in this range, in this greater than 1 micron range. So of course the properties will be different in both these cases because the microstructure is changing in both these cases. I hope I answered the question. Is it fine? Okay, thank you. Yeah. Yeah. Then we studied about the various strengthening mechanisms grain boundary strengthening, grain size, then how are they affecting the nanoparticles, or how are they changing the properties of the nanomaterials. We studied about that. Then grain size effect, that is Hall patch relationship, then we found out about that. Then finally we covered about superplasticity. What is superplasticity? Plasticity, the term means that the material shows ductile property. What is ductile property? The material can be stretched to a uh, to a to a level after which it fails. Like when you stress the material up to we can stress the material up to a level, after that it fails. That is known as ductility or plasticity of the material. Superplasticity means the plasticity level is too high for the material. That is, the material shows a higher plastic behavior. Means it can be stretched to a very high length, then it will fail. That is known as superplasticity. And we gave you some examples regarding superplasticity, and we discussed it a lot more details. You can always refer to previous courses regarding this superplasticity. Then another point we discussed about two things is that um, first, what we are thinking, okay, we have a material, we want the properties to be higher. We want the grains to be changed into nano size range. One thing, what we did is rolling. Rolling can help us to get the grain size to nano size range. But the disadvantage of rolling is that we are having a thick sample, we are rolling it into thin sample. So the sample morphology is changing. The thicker sample is becoming a thinner sample. So in order to get the nanoparticles, we are changing the sample morphology. Did you get it? That means, but all the applications will not require the sample morphology to be changed because I need a material which should be thick but should have nanograins. I can say that. I want that is my requirement. I do not want the material to be thin while having the nanosized. So how can we do that? So to save us from this problem, we have two other methods. One is equal channel angular extrusion method and one is high pressure torsion method. In these two methods, one focus is there. We are doing severe plastic deformation on the sample. This severe plastic deformation will in turn helps us to get nanograins. Why plastic deformation? Because plastic deformation generates defects or dislocations, and these defects or dislocations will act as nucleation sites for generation of grains. So the nucleation of the grains will be more. If the nucleation is more, more number of grains will be produced. More number of grains means the grain boundary density or the grain density increases because more number of grains are produced. That means if more number of grains are produced, that implies we are producing nanograins, right? So the equal channel angular extrusion and high pressure tension, they are applied to a material in such a way that nanograins are produced without changing the surface morphology or without changing the size of the material. So this will help in on our applications in our applications. But the problem with these methods is it is used for small scale industries. We cannot create large materials with this kind of techniques. So the industrial scalability is very less or very poor for these kind of methods. And another thing is we are creating severe plastic deformation to the material. So that means what is happening? We require more energy to create the severe plastic deformation. So that means more energy is required in these two types of processes. So these are the two disadvantages which we studied about these two processes. If you need to go into more details, you can always refer to the lectures or back in the sessions I have conducted. Yeah. So today we'll be discussing about three things. One is wear. Wear is another kind of mechanical properties which we take into account when we do various kind of research. So, wha- as an engineer, as a materials engineer, what we mainly see, we mainly focus on the mechanical properties of the material. That is to increase the strength of the material. If we increase the strength of the material, we want the material to be ductile, like this plastic, not super plastic. No, we cannot expect every material to be super plastic, but we want the material to be some amount of plasticity should be shown in the material so that it will not fail easily. So strength, ductility, and another point we look into where we consider the material is wear. What is wear? Wear is like when, for example, ball bearings or any other examples you see when the uh, something or the motor, for example in motor or anything, ball bearings, it needs to be changed on a regular basis, like for a year or two we need to replace it or change it, because the wear happens to those materials because of friction, regular friction, regular use of the materials get worn out. That is known as wear. And the thing is we cannot prevent wear we cannot totally eliminate wear. Of course there will be wear because there is friction in the material. The universe works with the friction, with along with friction. So we cannot prevent wear in the material. We cannot just say that okay, the wear is totally eliminated. But what we can do is to reduce the wear. We cannot fully eliminate a thing, we can reduce the thing. That we are what we are trying to focus on in wear. So for a wear test, we initially we cannot just go on, like if you want to know the wear of a material, for example, you cannot wait. Okay, you cannot just keep on continuously wearing it down to okay, let's wait for like 1 or 2 years to see the results. We cannot do that, right? So we need a method which will give us the wear rate way before than the application. So we can say that approximately if we use this method, if we use this much of time, this much of wear is produced. So we can get a comparative analysis like what material we give a better wear rate, because we'll keep the parameters same for all the material and we'll conduct the test. Then we'll get the final result. So we can compare. Okay, okay, the test was conducted for 3 hours. This material is getting wear more, and this material is not getting that much wear. So that means the material which is not getting that much wear is the material which we want to use, that is wear resistance. And another point to note here is that what we are telling, where we are using friction, the surface morphology is changing or the material is worn out. Material is worn out means the weight of the material is decreasing. There is loss of material. So weight loss is the parameter which you are looking into in the wear rates. There are various methods such as pin on disk, ball on disk method. I think Professor Pratap covered the pin on disk method, where the pin is the sample and there is a disk which is rotating, and the disk which is rotating, and the pin, sorry, the disk is stable and the pin is rotating on the sample, and then on the disk, and then we are calculating how much this friction of the pin on the disk, how much wear is there. We are calculating that. There can be two way. Either a pin is moving on the disk or the pin is stable and the disk is moving. Both are interchangeable. Then there are some other methods such as ball and disk method, and other methods you can have a look if you are interested. And one more point to note here is that I said that the parameters, because we cannot uh, calculate the wear rate for waiting for the material for 2 years to wear out, right? We are using to speed up the wear process. Like we have some standardized parameters, on that we conduct the test so that we get a comparative result of what is happening. And this standardized parameters is determined by the G99. ASTM determines the, as you have heard about ASTM standards, right? There is a standard book for all. Because the tests I conduct, tests someone else conduct in somewhere else should be of a level. Like we have to match our results. And how can we match our results? We have to keep the base or the parameters similar so that we can compare our results. Like, okay, this material is having a wear rate higher than my material, so we can compare that. That is given by G99. Let me just show you a G99 so that you can give you a, so that which can give you an idea of how this is taking place. Let me just show you that. Yeah, this is just a ASTM G99 book standard, as you can see here, G99. And the standard test method for wear of on pin on disc apparatus and pin on disc apparatus. Then here it will be given the summary of the test methods will be given. Here you can see the balls you are using, what is the diameter of the ball you are using. These were given, the roughness and hardness. Then the results will be given. Initially you can observe these things. Then finally you can see this is a pin on disk method of rotation. Then this is the parameters. This is the parameters which is determined, test parameters to be used in interpretatory test. These are the test parameters which is defined. So when we perform a wear test, we have to use these parameters to perform that test, so that we'll get a standardized value which can be comparable to other results. So finally, then they will be showing you about the surface finish, test specimens, what are the requirements. These are the parameters we are using. Then how to calculate the procedure is mentioned. Then calculations, how to calculate the wear rate or the weight loss, or how to plot that values. They are all given in G99, as you can see here. This is the one you are using for wear test of the sample. This method. Yeah. So yeah, so this is the question I have taken from the assignment. This question is quite easy. You can answer this question, but I want to show you a different perspective of this question. Like what information we are getting from this question. I just don't want to directly answer the question in the assignment. I will just give you a broad perspective of this question. Let's see. As I said, told you earlier, in wear, the first thing we look into is the weight loss of the material, because the material is wearing out, right? We require the weight loss of the material. And this is either sliding distance, because sliding, what is sliding distance? Imagine a pin on disk. We are just moving the pin on the disk to calculate the wear rate. So how much distance has the pin moved? That is known as the sliding distance of the sample. That's known as, and the weight loss. So sliding distance versus weight loss, or weight loss versus time, anything you can plot to which will give you this type of curve. For example, there are four materials A, B, C, D, and these four materials are plo- uh, conduct the wear test. The pin on disc wear test is conducted on these four materials, and finally you got this graph. Clearly, just for a layman language, clearly what you see, the weight loss is increasing at a higher rate for D, for material D, then comes C, then comes B, then comes A, right? So the in material D, the everything is remaining same. When you compare the results, as I told you earlier, the base should be same. That is the parameters, everything, time, sliding distance, everything, conditions should be kept same. Otherwise, there will be a different mechanism, because you cannot if we compare something, we need to keep the bases same. So here, every other parameters are remaining same. We are just comparing the weight losses of these four materials. As you can see here, the material D has a higher weight loss as compared to C, as compared to B, as compared to A. Just a minute. So that means the material D. the weight of material D is what? Is less than weight of material C after I'm talking about wear test, after wear test. Is less than weight of material B, is less than weight of material A after wear test. This is after wear test. That means the weight of material D is less. That means it has eroded more, or it has more wear has happened to this material, eroded more, or more wear has happened to this material. So what will be the, this is the weight. This is the weight. W, capital W is the weight. Do not confuse this with the wear rate. Yeah. So what will happen to the wear rate? Let's keep it by small w. So the wear rate of D will be higher than wear rate of C, will be higher than wear rate of B, and then will be higher than wear rate of A. So that means if the weight losses of a material is more, the wear rate will be higher. That means material D is not wear resistance, but material A is the highest wear resistance material because it is not wearing out more. The weight loss is not that much in case of material A as compared to in case of material D. That means the material A is more wear resistance than material B, is more wear resistant than material C, and is more wear resistant than material D. This will be the wear resistance plot that you can see here. Right? Did you get the question? Yeah. So this weight loss versus time, or weight loss versus sliding distance, determines the value of wear resistance, or determines how much of the sample is wearing out or not. Right? Did you get it? Okay. Let's go to the next one. Okay, ABCD has the same grain size. Okay, just tell me one thing. What does wear depend on? As I told you, wear depends on weight loss, how much material is being lost in the sample, right? So weight loss in turn depends on what? Strength of the material or the hardness of the material. If, for example, forget about wear, forget about everything else, just focus on hardness. Like a material is harder, a harder material will be difficult to wear, or if we apply some friction on the harder material and there is a softer material, and if we are applying friction to both these materials, what will happen? The harder material will be difficult to wear and the softer material will be easy to wear, right? So the harder material has good wear resistance, as you can see here. So the weight loss depends on the strength or the hardness of the material. And what does strength and hardness of the material depend on? The grain size, right? But you cannot say here that the material is having same grain size. Why you cannot say here? Because if the material D is wearing out more than material C, is wearing out more than material B, is wearing out more than material A, that means the hardness of material will be less, hardness of material D will be less as compared to hardness of material C, as compared to hardness of material B, as compared to hardness of material A. And in the previous slide, what I just told you, that the hardness of the material depends on the hardness or strength of the material depends on the grain size of the material. So the grain size of A will be more finer because the finer grains show higher hardness. So the grain size of material A will be lower than grain size of material B, and material D will be having the higher grain size as compared to these four materials. Right. So the grain size of the materials will not remain same because the grain size refers to microstructure, and microstructure will in turn affect the properties. So if you see a change in the properties of the material, that means there is something changing in the microstructure of the material. And in turn, microstructure means grain size of the material. So did you understand what I'm trying to say? Or am I able to answer the question? You asked in the group. Okay, thank you. Then let's go to the synthesis of nanostructured materials. Previously, we have been studying the synthesis of nanomaterials. We studied about bottom-up approach, top-down approach, different types of approaches. Now let's study about the synthesis of nanostructured materials. It's also the same. Like we are approaching in a top-down way or a bottom-up approach, but there are conditions are different in case of these producing this nanostructured materials. One more, the challenges which we discussed in the nanomaterials are like the composition. There should be uniform composition. There should be uniformity observed in case of size, shape, monodisperse particles. Almost the same things are observed when we produce nanostructured materials. The challenges which are observed in a case of production of this nanostructured materials are surface composition, boundaries between the particles. That is, as we know, surface by volume ratio is too high for nanomaterials, so they will tend to coalesce among each other or agglomerate among each other. So that is known as boundaries between surface composition, this composition. Then uniformity, like uniformly they the size of the particles, the shape of the particles, they're uniform or not during the synthesis. This is one more point to be taken into account. And porosity, if we are producing in nanoparticles, what is porosity? First tell me. Porosity is there is a gap in the proper arrangement of the proper if the crystal structure is there, then we're producing the grains. From the crystal structure there are grains, and if there is the grains are not fused properly with each other, or there is no proper grain boundary, or there is some material meshing, this is known as a porosity. Or there is an air bubble. Well, while producing this nanostructured material, a air bubble was introduced from the environment. Then there will be a porosity in the material, and this porosity, when we apply maybe mechanical strength, when we are testing some mechanical properties of the material, we apply some force to the material, the property will start the sorry the material will start failing from that pores only. That is known as porosity, problem due to porosity, and we want to avoid this because in turn it will affect the properties of the material. So this porosity will avoidance is the major challenge to in a nanostructured materials. Then one of the method which Professor Pratap discussed about is vacuum plasma spraying method. As you can see here, this term has three things: vacuum, plasma, and spraying method. Let me first discuss about these two things which you are quite familiar with. What is vacuum? Vacuum means the material. There is a material. There is a box in which vacuum. Vacuum means there is nothing in this. There is nothing. There is no air or anything in this box. That is known as a vacuum. And spraying means we have a substrate, we are using something or using a sprayer to spray on this material on this substrate. That is known as spraying. Then one more term is that is plasma. As you know, there are four states of matter, that is solid, liquid, gas, and above gas there is plasma state of matter. And plasma state is a very high temperature state, very high. You know, gaseous state, right? It is also considered as a high temperature state. The particles are randomly moving. In case of a if we consider in a gaseous stage, what is happening? The particles are randomly moving. They are not closely packed to each other. The atoms are not closely packed to each other, right? So in plasma state it is even higher, like 10,000 Kelvin, 20,000 Kelvin, in that range of temperature I'm talking about, where the atoms do not remain as atoms. They will become ions, positive ions and negative ions. That is known as a plasma state. So in vacuum plasma spraying, we are using vacuum, plasma, and spraying technique to produce nanostructured materials. That means we have a system here. We have a chamber here, which is being vacuumed outside, and there is vacuum. Then to create the plasma, we have anode and cathode. There is anode and cathode. which will provide the high energy to create the plasma. Then we have some powder feeder here, and a substrate here, because we need a spraying also. So there is a powder feeder, there is a cathode anode, and there is a feeder. So this feeder, what it is doing, there will be a transfer of electrons when we charge on from cathode to anode. The electrons will be transferred from cathode to anode, right? And this transfer of electrons will take up the particles and will spray on this, take up the particles from the feeder and will be spraying on this substrate, which will lead to the production of nanostructured materials. Let's see a video of what is going on. This is a video just to show you, give you an idea of how the vacuum plasma technique is done, plasma spray is done.
The plasma spray chamber is about 5 feet in diameter and 15 feet long. Inside, a plasma torch is mounted with the sample on the opposite side. The plasma torch consists of a water-cooled anode and cathode. An inert mixture of argon and helium gases flow around the cathode and through the anode, with a high amperage electric arc formed between.
As I said you, there is an helium or argon gas flow in the chamber. Why is it required? You would say that, okay, you said that there should be vacuum. Then why are you again saying that there should be an argon and helium gas flow in the chamber? This is to avoid the porosity, what I discussed earlier. So if what happens sometimes when you create high vacuum too, there is a chance of presence of small amount, literally small amount of oxygen particles or oxygen, and this oxygen will, because the materials have high surface to volume ratio, these materials will react with oxygen to produce the oxides. And if these oxides are produced and if these oxides are deposited on the substrate, they are not pure. This may create porosity on the particle. But we want the material to be pure from oxides. So to prevent these oxides, we are using argon or helium gas, so that the oxides will be, the oxygen present in the chamber will be removed, because argon and helium gas are quite heavy than oxygen. So they will be removed, and argon and oxygen will be present. But argon and oxygen are noble gases. They will not react with the nanoparticles, or they will not attach themselves to the nanoparticles to produce the oxides of the porosities. That's why we are using argon and helium gas.
them. This arc excites the gas to generate a thermal plasma reaching temperatures over 10,000 degrees Kelvin and creating a plasma plume over 6 feet long. The plasma vaporizes coating material instantly and propels it at velocities as high as Mach 2. Coatings are deposited
The velocity is in Mach 2. Mach 2, you know, fighter jets, they use the speed of Mach 2. In that velocity, we are depositing the material.
as thin, dense layers or as columnar structures that can be optimized for various applications.
So this was just an idea to give you an idea about what vacuum plasma spraying was. More details into this vacuum plasma spraying, you can always go through Professor Pratap's lectures. And I think there was not too difficult questions in the assignment regarding this vacuum plasma spraying. If you still have any doubts, you can ask in the group, or you can ask it now if you want. Yeah. So next we are having is what is ferroelectric. This is the final theory which we covered in this week. That is, what is ferroelectric material. Let's first talk about magnetic property and the electric property in a material. What is that? Like, what is magnetic? Let's first forget about electric property. What is magnetic property? What do you have said about magnetism? Like, if a material is magnetic, that means it will attract other magnets. That is known as magnetic property. And how do you know that a material is magnetic? We test it with magnets. And what is happening inside the material? There is north pole, south pole arrangement in the material. So when another magnet is approached to that magnet, there will be arrangement of north pole in one way, in south pole in one way. The material will be attracted to other material. that is known as magnetism, right? The North Pole and South Pole. This is defined in case of magnetism. But now you're talking about ferroelectric materials. Ferro means, as you know, it's ferrous, iron. Then electric materials. What is electric materials? In electric materials, there will be no North Pole and South Pole, because in magnetism we talk about North Pole and South Pole. So in electric materials, so there will be a charge difference in the material. A positive charge and a negative charge difference in the material will be there. Generally, materials are always neutral. If you see a material, generally they are neutral. Uh, they are not charged, or they will not show electromagnetism or anything else, if a material is neutral. But in ferroelectric material, this nominal charge is seen. Think about a metal. When we apply a potential to the metal, then only the charge, you can see that there is a charge difference, or it acts as a stores charge or anything. It can act as anything. But in case of ferroelectric material, there is no need of applying voltage across. It will automatically show the electric property in the material. And why this electric property in the material is seen? Because of any bond change in the material. Because all the materials are electrically neutral, right? When we like, think about crystal structure. When a material is formed, NaCl. NaCl is ionic salt. It's ionic crystal, but it is electrically neutral, right? Because the positive charges balances the negative charges. It shows no it's electrically neutral. It does not show any ferroelectric kind of properties. But we know that ferroelectric materials shows electromagnetism or anything, any other property, electric property, without the source of other external voltage. That is known as ferroelectric material. So there must be a difference in the positive and negative charge in case of this ferroelectric material to show that property, right? So what is this difference? Let's first see. For example, we will take the most ferroelectric material, or most known ferroelectric material, that is barium Ti3O. That is known as most the this is the example of the most the best material which is known to show the ferroelectricity. Just a second. BaTiO3, that is the barium, that is barium titanate, known as barium titanate. I was looking for the name of that material. That is barium titanate. Just a second. BaTiO3. So let's see what is you must have learned about crystal structure and how they are arranged. In this crystal structure, the barium atoms are arranged at the corners of the unit cell. See, at the corners of the unit cell. And in a unit cell, or a cubic unit cell, there are 8 corners. So there are eight barium atoms, and these 8 barium atoms, these per atom in the corner of the unit cell is divided with 8 other atoms, 8 other unit cells. So into 1 by 8. So this 8 barium atoms will be divided into 8 other unit cells. So 8 into 1 by 8 in one unit cell. So there will be one barium atom, right? Then in titanium, forget about this titanium for now. Then let's talk about oxygen. The oxygen is present around this face centered. And what are the number of faces in a cube? Six number of faces. So there are six oxygen atoms, and each oxygen atom on the face is divided with 2 unit cells. One is this side, and other is the unit cell which you're talking about. So into half, 2 unit cells. So this will be 3 oxygen atoms. Then we have titanium, and titanium is only present at the center. As you can see, only present at the center of the unit cell. So there is only one titanium atom present at the center. So three oxygen atoms, one titanium atom. So this gives the ratio 1 is to 3 is to 1. So 1 is to 3 is to 1. See, 3 is to 1. Oxygen is 3 and 1 titanium. So that means the charge neutrality is observed in case of that, because the number of atoms is remaining, number of positive charges is equal to the number of negative charges. So this means there is no charge, extra charge in the material. So how can I say that there is this material shows ferroelectric behavior? The center of the charge is different, because the charge present in the material will be centered around something that is different. So so the positive charge, so the positive and the negative, these are the oxygen atoms. What does oxygen atoms have? The negative two charge. So this negative charges oxygen atom is present at the center. The center of the charge is negative atoms is present at the center for all the charges. The equivalent of all the charges is present at the center. But this titanium atom is not exactly located at the center of the unit cell. It is a bit shifted, because the packing efficiency is not so high, because it doesn't, that's why it doesn't sit in the center of the unit cell. So there is, if the titanium atom would have sat in the center of the unit cell, then the charge balance will be proper, because the negative all the electro equivalent of the negative atom is present at the center, and there is a charge to balance this charge, there is a titanium atom. But this is not the case, because the titanium atom has displaced due to the lattice structure arrangement. So this difference in the placement of the charge, or this difference in the center of the charge, is creating a electric field in the material, and this shows positive and negative charge imbalance, and therefore the ferroelectricity is observed in case of barium BaTiO3. So, to learn more about this, you can always refer to Professor Pratap's notes. So, yeah, this much was for today's course. don't want to go more into details about this, because all the details are given by Professor Pratap. And I think all the questions regarding your assignments, I think, have been answered, because I cannot directly tell you the answer to the questions, but I will be helping you out with the answer, like how can you approach these questions. So I think most of the questions are being covered. If still there is any doubt, you are feel free to ask me, or I can help you out with those questions. Or if you don't find any options properly explained, you can always ask these questions. Not only for this session, for any other previous sessions also, it's fine. Or if there is no question, if there are no questions, then we can end today's session. Yeah, there's a question like, what is the structure of barium BaTiO3? So think about crystal structures. Think about the crystal structures. What are the different types of crystal structures do you have? We have cubic crystal structure. We have simple cubic, face-centered cubic, body-centered cubic. So what do you think? This is not a simple cubic, because simple cubic has atoms all only at the corners. This is not a vertices. This is not a simple cubic. This is not a then you may think this is a face centered cubic, but you see atoms are present at the face centers, as well as atoms are there is another atom present at the center of the unit cell. Another point to note here is that See, when we define the crystal structure or BCC, FCC, or any other crystal structure, how do you define? Those crystal structures are defined if the materials are in all the places, like the FCC, the face center ones, the simple cube, the vortices ones, or the body center ones are same. If the atoms are same, then we can say that okay, this shows BCC, this shows FCC. But what is the thing here? Do you think the materials are same along all the directions? Can you justify that? Okay, this shows FCC. I can question you. Okay, there is barium atom present at the vertices of the unit cell, but there are oxygen atoms present at the face centered. This is not a BCC. Then you will say, okay, this is this is not a FCC. Then you can say, okay, then it's BCC because the titanium atom is present at the center. But the titanium atom is a different kind of atom than barium. When we define BCC and FCC, we define all the materials as same. The FCC atoms will be same as the corner atoms. The body center atom will be same as the corner atoms, right? But here everything is different. All the material, all the atoms are different. So of course, as you said, is it tetragonal? The material shows a tetragonal type of symmetry. Shows a tetragonal type of symmetry, but we cannot say that it is a tetragonal unit cell because in a unit cell, all the material should be exactly same. What is a tetragonal unit cell? Alpha. There is a relationship between alpha, beta, gamma, and there is a relationship between A, B, C. It shows that value a the tetragonal has some relationship and it shows this relationship between these parameters, lattice parameters, but it cannot be said as a tetragonal unit cell because all the atoms are different in that. I think I hope I'm able to clear out the answer. If you still some doubts, there is something called as space group point groups. That is a very different kind of concept. I will not go into details there. It shows a space group of tetragonal, but it's a perovskite structure. It's a different kind of structure because we cannot define it as a tetragonal structure, so it shows perovskite structure. That's a different kind of structure. If you want to go detail into that, you can always refer to the internet. It will be helpful for you. I think I am able to answer the question. So yeah, if you have no further doubts, then we can end the session. Or if else doubts are there, then I'm happy to help you out. Okay. So thank you, Ramesh. Thank you for your doubts. Thank you all for attending. So these lectures are available on YouTube. You can always go back to these lectures of what I explained, and you can always feel free to ask the doubts if possible. So yeah, that's all for today. Thank you so much for attending. Have a great evening.